If you are, then you set a flag in your data that this is not real data, and then you encrypt a counter. And that means the attacker, without knowing your key, won't be able to understand that steganography is taking place. So the same idea works for OpenBSD. It has a very different way of generating initial sequence numbers. There's nothing to do with connections. There's just one global setup. Once the requirement is that there should be no two consecutive initial sequence numbers which are close to each other, then you have problems of collision. The way it achieves this is for the first half of the 32 bits, it takes a counter and then encrypts that using a block cipher. One of the properties of a block cipher is you will never get duplicates in output if you don't have a duplicate in input. And with a counter, it means that you get, in this case, 2 to the 15 before you see any collisions in the output. But given any of those, you shouldn't be able to predict the next one without knowing this 1024-bit random key. Just like Linux, it rekeys also every five minutes. And that's what the top bit is for. The rekey, rather than a counter, it's just a bit. And this means that when a rekey happens, you will never have two outputs that are very close to each other. The bottom half is replaced with some output of RC4, which is the random number generator that OpenBSD uses. This is not a block cipher, it's a stream cipher, so there can be collisions. The other thing that's added is a 0 in between the block cipher output and the RC4 output. This is because the RC4 output could change from all ones to all zeros, and the block cipher could change from all zeros to all ones. And then you'll have, without that 0, two initial sequence numbers that differ only by 1. With the 0, you guarantee that they're more than 2 to the 15 apart. Again, if you want to encode steganography in Linux and OpenBSD, you follow that. RC4 is easy. It looks like random numbers, so that's exactly what you put there. You do the standard tricks to encrypt your message and make sure it looks like random, and then you embed that into the bottom 15 bits. The top 15 bits is harder. The guarantee that a block cipher gives you is there's never going to be repetitions. Whereas if you're encrypting different messages, if you encrypt the same message twice with the same initialization vector, you will get the same thing out. And that should never happen. So what you have to do is encode arbitrary data into a pseudo-random sequence, such that there's no duplicates. This starts off as being easy to do, but the problem that comes in is there might be packet loss. And the obvious ways of doing this mean that as soon as you lose one packet, then you lose everything. So in the associated paper, I show the algorithm that is used for doing this. Okay. And now for something completely different, or at least it seems that way. There's been a recent paper which shows that many machines have different clock skews. This is because every machine has a clock crystal in them, and they're not all perfect. Over time, they will drift away from each other. They're also very stable. So if you're off by 1 millisecond per second now, then if you go to a different country, then you're probably going to be off by 1 millisecond per second. This means that if you take your laptop to an access point here, and then you want to become untraceable, and you take your laptop somewhere else, you make sure you're not using any of the same applications, and you're obviously using a different IP address, then to a certain extent you can still be tracked. This graph shows a collection of TCP timestamps from a few machines I've accessed, and you can see that they do differ by a significant amount, and a measurable amount after 400 seconds. There's a significant amount of noise. In the top ones, you can see that there's rough edges, but in the bottom ones, there's a lot of noise. This is because TCP timestamps can vary in speed. There's nothing in the specification that says how fast they are, just that their time, they can vary between 1 hertz and 1 kilohertz. In the case of Linux, I think it's between 100 hertz, and those are the bottom ones, and 1 kilohertz, which are the top ones. So I'm interested in reducing the amount of noise. I mentioned that when Linux generates initial sequence numbers, it adds on the time in microseconds. So that's a 1 megahertz clock, 1,000 times faster than the TCP timestamp. Another option is the ICMP timestamp. This is where you send a packet to a machine, and then you'll get a request, a reply, which is the time in 1 kilohertz. You'll notice this is the same number of machines as last time, but there's a lot less variation. In fact, all the machines that were NTB synchronized have been clustered into those middle bars. That's because the timestamp that's used in TCP for the TCP timestamp happens before the NTB synchronization, whereas with ICMP, this happens from the get time of day system call. So you'll remember this graph from before. This is where I showed that Linux uses time information when it's generating initial sequence numbers. And also I pointed out that if you look up from the packet sent with 3 milliseconds different, you'll get to 3,000, and that corresponds to microseconds. There is a subtle difference here. The time difference on the x-axis is time according to when the packet is received, and the initial sequence number is the time according to the machine that sent it. That means you can use this to estimate the clock skew. And here's the output of that. And first you'll notice that it has the same problem with NTP, but it's a lot smoother. And this does give some options for avoiding the NTP problem. NTP is designed not to track short-term changes. It takes about 6 hours once it detects that the clock is probably incorrect before it corrects that. That's to stop it chasing the air conditioning, because a clock crystal will change its speed subtly when the temperature changes. That means that if you zoom into these graphs, you'll be able to see that the clock skew changes, and then the NTP will synchronize it. You also have to worry with the initial sequence number that there's going to be rekeys. This is quite hard to deal with because it's perfectly possible for the initial sequence number not to change when there's a rekey. The other thing that's a lot easier to handle with is when there's overflows. An initial sequence number is only 2 to 32 bits, and when you have a 1 megahertz clock, it is going to overflow. That's very easy to detect. As soon as you see 2 packets from the same source destination port IP address that go from a high number to a low number within a rekey period, then you know that there's been an overflow. Okay, so in conclusion, there's many proposed steganography schemes that are detectable. The main reason is that they look at the specification, which says that this field can be anything, it could be random, and then assume because it looks vaguely random, it is random. In fact, this isn't the case. In the case of Linux, the initial sequence number is not random for very good reasons. That's to stop collision. The IP ID is not random for random reasons. And if you want to build a undetectable steganography scheme, because you're worried about someone watching the network traffic, then you have to follow the specification backwards and make sure there's no way of detecting that. So if you look at the paper I've got associated with this, it's not in the proceedings, but it is in my website, then I've got a suite of tests that should tell the difference between random data and appropriate IP IDs and initial sequence numbers. This could also be used for fingerprinting. And the other thing I mentioned was the physical device fingerprinting. If you think you're untraceable because you move your computer to a different continent, then that may well not be true. If you're worried about someone fairly powerful tracking you, then this should be a concern. You could try to turn off all sources of timing information. The obvious ones are ICMP timestamps are easy to turn off, as are TCP timestamps, but initial sequence numbers aren't. So you could look at options like the OpenBSD randomization of sequence numbers firewall. That has some possibilities, but I'm looking at other ways to extract timing information even from that. So if you're worried about that, you have to make sure that there are no sources of timing information that you don't expect. So I'll finish a bit early now, but I'm happy to answer any questions. Thanks.
I guess my question is pretty simple in the end. Where is all this being used?
That's a good question. I am not aware of any case where a covert channel in the computer system has been used for profit. With the only exception is a project I did a couple of years ago where I slightly bent the rules in a programming competition in order to win an Xbox using a covert channel. And despite there being a lot of concern in the military for covert channels, since the 90s there's been billions of dollars spent on trying to remove covert channels. I don't know of one case where they've actually been used. But if people were using them, they probably wouldn't say.